All right, here we'll prove this kind of nice theorem. If you have a field, then every ideal in the ring of polynomials over that field is principal, meaning again that it's generated by a single element. So let's prove this theorem. I'm going to take a polynomial px in my ideal of minimal degree. So I'm going to look at all the polynomials in I, and I'm going to find one of them that has the smallest possible degree. What we'll end up proving is the ideal I is generated by that single polynomial, meaning that I have a principal ideal. So there are two cases to consider. What happens if the degree of p is equal to 0? So if the degree of your polynomial is 0, then your polynomial is simply just a constant in your field. Now, if your constant a is 0, then your ideal is the 0 ideal, and that's kind of trivial. I don't really want to worry about the 0 ideal. If your constant a is non-zero, since we're in a field, the inverse exists. So then I have 1 is equal to A inverse. A is in my ideal. Therefore, A inverse is also in the ideal. Part of the definition of ideal is if you take something in your ideal and multiply it by anything else in the whole ring, you get back in the ideal. So A inverse is in my field, so A inverse is in my ring of polynomials. This shows the number 1 is in my ideal. What that means is my ideal is actually just the entire polynomial ring. Once you have 1 in your ideal is everything. So my ideal I is the entire ring of polynomials. So it's generated by a single constant a, and we indeed have a principal ideal. Okay, that was the case when the degree of p was 0. Let's see what happens if the degree of my polynomial is bigger than or equal to 1. So in this case, I'm going to take f to be any other element in the ideal I. Let's take any other polynomial in your ideal. Well, what we have is f of x is equal to p of x times q of x plus r of x. What I just did is I divided f by p, and I got some quotient and some remainder. Now this is true where where q and r are polynomials, and the degree of r is less than that of p. So that's just division. You could rewrite this statement. I'm going to rewrite it just subtracting this term. So I get p of x, q of x. That's equal to r of x. Now, f is in my ideal. P is in my ideal. So this is in the ideal I. P is in the ideal I. Therefore, this whole term, again, in my ideal I. So this whole left side is in my ideal. Therefore, this is also in my ideal I. Now, r of x has a degree that's strictly less than that of p, and it's in my ideal. So the only conclusion is r of x is actually the 0 polynomial. If it wasn't the 0 polynomial, if it was an actual non-zero polynomial, then its degree would be less than that of p, but we specifically took p to be minimum degree. So no option for that. Thus, my function f of x is in the ideal generated by p. It's in the ideal generated by p because it's a multiple of p. This remainder term is 0, so f is p times something else. That's exactly what this ideal generated by p is. So we're done. So what this shows is I took an element f in my ideal. I showed it was in here. So I guess technically I showed that my ideal is a subset of the ideal generated by p. But of course, the reverse inequality holds almost trivially. So thus, I is the ideal generated by p. All right, there's our proof. Kind of a nice result.